Up until now, our code has stayed internal to the JVM. At this point, we're going to branch out and start communicating with the environment the JVM is running in. We'll do this by taking advantage of resources. Resources can be files, network connections, database connections, streams, or sockets. We use these resources to interact with file systems, networks, and databases to exchange information. It's impossible to access a resource without first needing to address exceptions, whether we want to deal with them or not. I've only briefly touched on this subject, using try-catch blocks and printing a stack trace when an error occurs. When you're dealing with external resources, exception handling becomes much more important, so I'll be covering a lot more aspects about exception handling in this section. When you instantiate one of Java's file access classes, Java will delegate to the operating system to open a file from the operating system's file system. This then performs some or all of the following steps. Check if the file exists. If the file exists, check if the user or process has the proper permissions for the type of access being requested. If this is true, then file metadata is retrieved and a file descriptor is allocated. This descriptor is a handle to the opened file. An entry is made in the file table or file control block table of the operating system to track the opened file. The file may be locked. The file may be buffered by the OS, meaning memory is allocated to cache all or part of the file contents to optimize read and write operations. Java uses a file handle to communicate with the operating system for file operations it wants to perform. Many of the methods in Java make opening a file look like instantiating any other object. You don't have to call open on a file, so it's easy to forget that you've really opened a resource. Closing the file handle will free up the memory used to store any file-related data and allow other processes to access the file. Fortunately, most of the Java classes you'll use to interact with files also implement an auto-closable interface, which makes closing resources seamless, but it's still very important to be diligent and to understand the consequences of keeping file resources open. I'll be discussing this a lot more during the exception handling videos in this section. Java has what seems like a very confusing and large series of classes in many packages to support input-output. I'll be covering the most commonly used types, but first, let's talk about Java's somewhat confusing terminology, which includes I/O, NIO, and NIO2. First, I/O is a term for input-output, and Java.io is a package that contains the original set of types that support reading and writing data from external resources. NIO was introduced as non-blocking I/O with the Java.NIO package in Java 1.4, as well as a few other related packages. The communication with resources is facilitated through specific types of channels and the data stored in containers called buffers when exchanged. NIO.2 stands for New I/O and is a term that came into being with Java 1.7, emphasizing significant improvements to the Java.NIO package, most importantly the Java.NIO.file package and its types. Does this mean everything in Java.io has been replaced with new functionality in the Java.NIO packages? No, but in many cases there are different means for doing the same thing. NIO2 introduced the path and file system types and some helper classes such as files, paths, and file systems that do make some common functionality for working with operating system file systems, much easier as well as more efficient, delegating work to native systems. Where functionality overlaps, I'll show these to you side by side. You'll likely see a lot of legacy code using the classes you see on this slide in the Java.io package, so buffered input streams and file writers and so on. But I also want you to see the NIO2 types at work, many of which provide more support for functional programming. Let's get started.